Some of you have been here once or twice and have heard me talk about theory of the strong nuclear force, the theory of elementary particles, string theory, quantum gravity, lots of fundamental theories in physics. And as Laura said, this talk is a little different. I'm going to discuss the issue of a final theory or a theory of everything. But I'm not going to tell you or describe to you a final theory of physics or even a potential candidate for a theory of everything. This is a slightly different kind of talk. This is going to be less technical, more metaphysical if you want. Should be easier to understand and participate in discussion. Given talks like this often as part of a more general talks, and they tend to last about 15, 20 minutes. Louder. Okay. What do I mean, first of all, by a final theory of what? Well, I'm a physicist. We're talking about a theory of everything. We obviously mean the theory of physics, which underlies everything we believe, or at least everything that can be approached scientifically. But what I'm really discussing is what we tend to mean by a theory of everything is not a theory of every detail of the physical world, but rather a understanding of the fundamental laws that underlie, in principle, everything that we might be able to observe, measure. So in that category, we have gone over the last few centuries from Newton's approach to a deterministic mechanical theory of the world to a more modern approach based on fields, electromagnetic fields, on a relativistic version of the mechanical world, the quantum mechanical revolution, which this year is exactly 100 years old, that enabled us to understand atoms and molecules and elementary particles. In the case of cosmology, which is also a fundamental theory of the universe, we've gone from almost no understanding of the structure of the universe to a quite detailed theory of the history of the universe from a very early period till now. A final theory would be a complete and sufficient description and understanding of the basic principles of physics that underlie our understanding of matter and the forces between constituents of matter, and as well as the history of the universe, from beginning to understanding how it will end, whatever that means. So that's sort of the context. Now, we don't have such a theory, and one of the first questions I will pose and try to make a few remarks about is will we someday achieve a final theory of everything in that sense? Does such a thing exist? Second, I'll try to discuss briefly the question of whether we have any chance of discovering such a theory, understanding the basic principles that underlie all of physical reality. Maybe we can, maybe we can't. And I'll end with some perspectives on our ability and will to do that. So let me start with, physicists like to construct models for whatever phenomena they're trying to understand. The models tend to be simplistic. We sometimes talk about the spherical cow approximation. Cows are complicated. You're placed them by spheres, they become much simpler. Models are very useful because they focus how you think about a given subject. They give you often the ability to carry out rigorous mathematical descriptions simplified descriptions of the real world. make predictions that can then be tested. So I want to start by giving you my model of the structure of knowledge and ignorance, to put into context what it would mean to have a final theory. Now, there is a well-known model for the structure of knowledge, which I call the onion model. Now, knowledge, universe, the realm of physical reality is like an onion. We observe the onion, but we peel away the onion to get to the core and the ultimate understanding of reality. This model I don't like at all. It brings tears to my eyes. It explains nothing. It assumes, by the way, that yes, there is a final theory. After all, an onion, you peel it away, you get to the core, it's gone. You've gotten to your goal. So it assumes the answer to the question we're posing, and it doesn't make any predictions. So I'll give you a different model. Turn the onion inside out. We live in our search for understanding physical reality in a sea of ignorance. And so you imagine a ball, a sphere in this sea of ignorance. The ball defines the region of physical reality that we understand. And we're continually pushing that sphere of knowledge out into this sea of ignorance. Now, okay, that's sort of the inverse of the onion. And I'm going to use this model to explain something you all know and to test its usefulness. So we've been, as a species, pushing out into the sea of ignorance, especially with the invention of the scientific method for thousands of years, but more recently with science, hundreds of years, and expanding the sphere of knowledge. Done quite a bit. An enormous amount of knowledge that we've accumulated. Organized knowledge based on simple patterns that have been synthesized into regularities, into laws, principles, in very much this reductionist fashion that science, especially physics, operates. And knowledge increases. Now, most of the knowledge we've accumulated as a species over the centuries is accessible to all of us, especially today. Wikipedia, libraries, books, the internet. So even, if we're not, all of us, of course, are not conversant with all the knowledge in the sphere, it is available, and we can use it in pushing the sphere forward into the sea of ignorance. So knowledge increases, sort of like the volume of the sphere of knowledge, outward into the sea of ignorance. But in this picture, ignorance also increases. Right? At the frontiers of the sphere, bordering the areas where we don't know what's going on. Okay? That's that ignorance that we're aware of. Jackie, my wife, doesn't like me talking about ignorance because it's too prevalent in our society today. And I famously, often make a statement that the most important product of knowledge is ignorance, which I explain means that what drives science forward, what we are working on, are exactly trying to push knowledge outward and to turn ignorance into knowledge. What is valuable, this ignorance is really valuable, it fuels science. But what I really mean by ignorance are unanswered questions that we become aware of because we have enough knowledge to realize that there are new questions. Most of the questions that we ask today were not asked scientifically, at least when I was a graduate student. For example, we asked about the origin, the beginning of the universe. How did the universe begin? What were the initial conditions? That was a question for not scientific exploration 60 years ago. It was always has been a question that people asked, but philosophers, religious prophets, but not scientists. You couldn't, 60 years ago, easily get a paper published on the theory of the beginning of the universe. But now it has become a scientific question. So those are the questions that define our knowable ignorance, are at the boundary of the sphere of knowledge. They are the knowable unknowns. As Rumsfeld, Bush's defense secretary, famously said, they're the known unknowns. Those we're aware of. Well, they pose the questions for science. And then there are the unknown unknowns. We know that there are probably questions that we don't even know how to pose scientifically or even pose in any way. And history of science has shown that as we push out into the sea of ignorance, new questions arise. In fact, ignorance increases. The more we know, the more we realize that we don't know. Now, I'm sure all of you have experienced that as a fact in your life. And students sometimes complain, I thought I would go to school and I'd know everything, they'd give me all the answers, but they realize, and we as scientists realize that the more we know, the more we seem not to know, the more questions there are. So this model fits very well then, right? The sphere of knowledge grows like the volume. The knowledge grows like the volume, and the ignorance grows like the surface area. It's only on the boundary between knowledge and ignorance that we understand the questions, the ignorance. So knowledge grows, understanding grows, but at the same time, ignorance grows, or new questions arise. And, however, we seem to feel wiser. Because after all, knowledge is increasing like the volume of the sphere. Ignorance is also increasing, but only like the surface area. And as you know, volume increases faster than surface. So wisdom increases. So this model fits together with everything we experience as a species or as individuals. We know more. We're aware that we have more questions, more ignorance, and yet we feel wiser. So now let's apply this model to the question, could there be a final theory of physics or fundamental science? Well, that in mathematical terms, geometric terms, is a question of whether this sphere of knowledge is compact, finite, or non-compact and infinite. So now let's picture that. Think of the surface of the Earth. And we're here in Santa Barbara. We have a sphere around us, this room, say, and we push out. Because the Earth is a sphere, this two-dimensional sphere, is compact, is finite. Eventually, we keep pushing, we cover the whole Earth. The surface of a sphere is a compact, finite size geometrical object. Now, in the past, many people thought the Earth was flat. There's still some people who think the Earth is flat. Earth is infinite. It's not compact. You keep pushing a sphere, this room, out on the flat Earth, you go forever. So, and geometrical objects can be compact, finite area, finite volume, or non-compact, infinite volume, infinite area. A final theory would mean that the geometry of knowledge is compact. Final theory would mean that we would run out of ignorance. So we've reduced the question is the sphere of knowledge compact or non-compact? Is it like the surface of the earth or a flat sheet? It goes on forever. In fact, we have an historical example of a realm of knowledge where this issue arose for our ancestors. Not that long ago. If you look at maps of Europe, typically 1,000 years ago, medieval maps of Europe, you will see that they are exactly following this model. They are a two-dimensional sphere, mostly of Europe up to some place in Russia, the Roman Empire, parts of North Africa. That was the world. And beyond that, there were oceans and land areas. That was part of the Sea of Ignorance. And they're pretty empty. And over the last 1,000 years, people explored, moved out, or Europeans. There were people, of course, who didn't have maps that have survived, at least, living in these areas. But from a Eurocentric point of view, Europeans moved out, explored these, carried out the science of exploration of the Earth's surface, and eventually ran out of ignorance. Today, we have mapped the surface of the Earth to a precision of meters. Maybe the US military has mapped it down to centimeters. And it's available on Google Maps. You can find a pretty good map of the whole Earth, surface of the Earth. So in the case of exploration of the surface of the Earth, there is a final map. The job is over.
Not of the seafloor.
What?
Not of the seafloor.
I said the surface. We can go down too, and that is harder. But, the Earth is finite. Exploratory societies went out of business. The science of exploring the surface of the Earth, in some sense, was finished. And that's sort of what I'm talking about. Could we imagine such a thing in the realm of physical reality, in the realm of physics? I don't know the answer. I'm totally agnostic. I don't know how we and there's obviously, in my opinion, no way of giving a definitive answer. It could be compact, like the surface of the Earth, or it could be infinite. If it was compact, however, there is a way we would begin to suspect that that was the case. When people started exploring the surface of the Earth, after a while, very early on, they could see the horizon. They could see that the Earth was curved. Of course, the really clever people understood for many other reasons why the Earth was a ball and not an infinite plane. As far as I can see, there is no sign of curvature. What would be a sign of curvature? Sign of curvature would be that we were beginning to run out of ignorance, run out of new questions. Just like when we start moving around the surface of the Earth, the area, the size of the boundary of the sphere of knowledge gets smaller. For a while it gets bigger, 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 until you sort of get to the equator, and it gets smaller, smaller. eventually shrinks to zero. But as I said, it's my experience, and I think that of all of us, so far, the more we know, the more we realize we don't know. The larger the boundary between knowledge and ignorance is growing. I think we would begin to notice if the opposite was happening and we were running out of new ideas and new grant proposals and new thesis projects, but we're not. But it could be. Maybe we just haven't had enough time to explore. I'm really agnostic. I see no. It's just that it's clear at the moment that there's no sign of the indicators, which would be very powerful if we were beginning to run out of questions, or beginning to notice the horizon of the geometry of knowledge. Now, but it could be that we will, just as we did in the exploration of the Earth. What would that mean? Well, it wouldn't be the end of science by any means. There are a number of scientists who are working in this sort of reductionist mold of looking for the underlying fundamental principles from which everything else in principle emerges or could be explained, is very small. Most scientists are using that knowledge to push our understanding of phenomena which we broadly think falls within the realm of these reductionist principles. And that has an infinite structure of a different magnitude. For example, most physicists work on what is largely called condensed matter physics, atomic physics, molecular physics, chemistry, materials, all of whose basic principles, those are quantum mechanics and electromagnetism, the existence of the atomic nuclei and electrons that we understand, we think, completely at the level that is necessary for the exploration of ordinary materials and matter and chemistry. But there seems to be no reason why that pursuit, which is absolutely fascinating and gives rise, continually produces new structures, new materials, could not go on forever. There could be very well infinite and infinitely interesting combinations of the materials we understand and our consequences of the underlying principles that we understand. So the reductionist goal could end, would not be by any means the end of science or of understanding of the complex structures that arise from basic principles or of applications. Okay. Assuming that there is a final theory, is there any chance that we are smart enough to find it? And this is also a very interesting question. We're asking now questions that seem awfully complicated. What is the quantum nature of space and time? How did the universe begin? We can seem to require more and more mathematical tools that are abstract and far removed from simple arithmetic. Why are we so arrogant to believe that this species has only been around for about 100,000 years, with 1,000,000 years maybe, is evolved in such a way to be smart enough to answer these questions or find a final theory if there is one, or continue to explore forever if there isn't a final theory? it's pretty arrogant to believe that. I mean, we are products of evolution and only removed from yeast, which we share a good part of our genome with by a few 100 billion years of dumb evolution. We know very well that some of our friends, other species, are quite limited in their ability to do science. I always remark that I've been unable to teach my dog quantum mechanics. Now, we're not that different from dogs. We understand that dogs are limited, that they are unable to understand quantum mechanics. They will never be able to understand quantum mechanics. So what gives us the right to assume that we are smart enough to understand the underlying basic principles of nature? What was the advantage, the evolutionary advantage for us to develop the ability to do that? So you look at it from that point of view, you'd be pretty pessimistic. Right? Dogs have limitations, cats have limitations. Yeast has a lot of limitations. Why? So from that point of view, either if there is a final theory, or especially if there isn't, at some point we're going to run out of our ability to keep going in the pursuit of understanding physical reality. Okay, I'm not that worried for a bunch of reasons. First of all, what sets us apart from the dog and from yeast is what is really special about our species, I believe, is the language. It's clear that we are the only species that possesses, at least in language in its full strength. I mean, other species have some form of communication for various reasons, but not language as we understand it. Mathematics, we have realized in the last few hundred years, in some sense, is the language of physical reality, is the language of physics. Galileo famously made that remark early on in the scientific revolution. Mathematics is really language taken to the extreme. It's the highest form of language. And both language and mathematics have, unlike the rest of our abilities, are a certain infinite capacity. Chomsky famously explained that language is remarkable in the sense that a baby, a human baby, with no real training can pick up a language simply by hearing his parents or other humans talk, and very rapidly can utter sentences that have never been uttered before. Language has that infinite capacity. Any of us, with enough time, can utter a sentence that has never been uttered before. Mathematics has that and even greater infinite capacity. Now, that's something important, I believe. It's not perhaps enough to give us reassurance, because there are many kinds of infinities, and maybe that's not sufficient. But it's remarkable, and so far has proved for us as a species quite adequate to go pretty rapidly and pretty far in enlarging the sphere of knowledge. Here too, we can, my optimism can, at least the current moment, be supported by experimental evidence. Let's imagine that we're like dogs. And at some point, some of the questions we're asking, the quantum nature of space-time, how do black holes really behave? How did the universe begin? Some of these questions we're getting to the point that, like dogs, we simply don't have the capability to answer. That could be the case at some point. I don't think we're close to that now. And the experimental evidence is that if we were getting close to the point where the questions we were studying and trying to answer were like dogs trying to understand quantum mechanics, we would observe the following. It would take longer and longer for graduate students to graduate. Graduate students, typically, and sometime in their 20s, get to the frontiers of knowledge. They have to learn a lot to explore, to get close to where the interesting questions are, close to the boundary of knowledge and ignorance. But the time they take to get there hasn't increased at all very much over the last few hundred years. That's remarkable, actually, because there's a lot more to learn, you would think. There are two reasons why that's still the case, that people, brilliant young students, can, by their middle 20s, start making significant advances and into the sea of ignorance, just as they did 400 years ago. One of the reasons is that we've gotten a lot better at teaching them. We understand things so much better. What's really important to know, how to teach, how it all fits together, how reductionism works. So we can indeed educate people and get them to where we are 400 years after we have been rapidly accumulating knowledge. But second of all, it also means that as hard as it is sometimes for us old fogies, we look, the students now have to learn mathematics that wasn't invented when I was a student. I also have to learn. And it looks awfully hard, but for them, it's just as easy as it was for us, or for Einstein, or for Maxwell, or for Laplace. They all manage. So there's no sign that we're getting close to the point where the questions are really more difficult in a fundamental way. No sign that we're becoming like dogs trying to understand quantum mechanics. But maybe that'll happen in the future, 50 years from now. It'll turn out that we start noticing that students, in order to get to the point where they can participate in ongoing research, will be in their 30s and 40s and 50s and so on. That could happen. But then, I believe, and even before, we'll push on by taking advantage of machines. We already do that, of course, with computers. We're beginning to do that with AI. If that doesn't completely work, we can always start tinkering with our genome. So I'm pretty optimistic in Homo sapiens being able to push forward towards either a final theory or forever. So that's more or less what I wanted to say. A lot of it is optimistic. Both goals, a final theory or an infinite sea of ignorance, are wonderful explorations, an exciting future. The only place where my optimism is somewhat tempered is in the support that science requires from society. So one thing that definitely is happening, especially and accelerating, is the increase in time scale and in financial resources necessary to push fundamental science towards further into the sea of ignorance. That's certainly happening in the two areas which are part of this process: cosmology, astrophysics, and elementary particle physics, where particle accelerators are becoming both expensive, they already are expensive, they're becoming slightly more expensive, but also the hardest problem is that the time it takes to carry out these projects becomes a bigger and bigger part of human lifespan, and requires more and more resources. The same is true in astrophysics and cosmology, and here, again, the future is unclear. I can only hope. Whenever I talk about this, I end, as I will now, but open it up for discussion with Hilbert's famous quote, which is on his gravestone in German, but in English: "We must know, we will know."